Have you ever imagined a future where chips and Moore's law are giving a whole new meaning? Hello, my name is Ming Zhan. I'm from Synopsys. I'm here to speak to you about making system of chips for the SysMoore era. Today, I'd like to go over 4 chapters for this talk. First, let's look at the trends of manufacturing that are really driving the innovation of chip designs. Secondly, why are people making system of chips? Thirdly, how EDA can help as a catalyst for innovation. And finally, what's the journey ahead? Manufacturing trends. In the last 50 years, logic and memory scaling have been the key driver for scaling and advancement of semiconductor development. The curve is very linear on an exponential scale. In the future, according to data from TSMC recently, 3D interconnects could be the catalyst for scaling beyond the miniaturization barrier. Packaging has traditionally been a follower. In other words, chip design or IC design has always led packaging. The packaging and ICs are now working hand in hand or walking left foot and right foot. They're really becoming a continuum because the manufacturing and design of the chip and packaging have to work together, regardless whether we're talking about organic substrates in 2D or interposers in 2.5D or 3-dimensional stacking. There are many manufacturers for advanced packaging. One way to look at it is this creates complexity for design enablement. Another way to look at it is this actually creates a really good possibility for design innovation because now designers have a lot of technologies to work with. So why do companies want to create system of chips? AI, in particular, AI training has been pushing the limit. According to one data point that's published this year, the amount of memory that's been made available to AI training has been doubled about every year, although the size of the model has been increasing by about 100 times or a little bit more every year. So clearly, the application wants more than what the hardware can offer. We have had the good pleasure of being driven by technology in the past few decades. That's the classic Moore. It continues to progress, even though it progressed a little bit slower recently than before. And that is the era of SoCs, or system on a chip. With the AI creating more demand, there are also more opportunities coming from systemic complexity, such as architecture innovations and 3D IC innovations. This is really becoming a booster pack that creates the new era of SysMoore. And this is also the beginning of the age for a new type of SoC that's system of chips, as opposed to system on a chip. Why do companies create system of chips? Generally speaking, there are 2 reasons. One reason is to integrate chiplets or smaller chips that are coming from different process nodes so that the end product, the new bigger chip, provides the best-in-class functionality at the top level. The other reason is to break down or partition a bigger chip into smaller pieces in order to accomplish higher yield or lower cost. If it's done correctly, it's possible to accomplish a faster time to market, a higher degree of security, regardless whether you're doing integration of chiplets or disaggregation of chips. Here are the common commercial use cases. Networking SoCs, switches, or co-packaged optics modules tend to work really well for integration because the underlying ingredients are usually coming from different process nodes. So you want to combine the strengths of the right process node for the right block. That's where integration makes a lot of sense. For big chips, such as server chips or AI chips, they tend to be big. For cost reasons, for yield reasons, it makes sense to break them apart or disaggregate them. Now that we understand the trends of manufacturing from 2D to 3D and the reasons why the new age of system of chips are important, let's think about why EDA can be helpful to manufacturers and designers. In other words, I like to say EDA is a catalyst for future innovation. Let's look at the journey of creation for chip designer. EDA stands for Electronic Design Automation. It really enables a designer to go from A to Z. A being the beginning, which is explore. Whenever you start a design, you want to explore your options. You want to look at your chiplet choices, IP choices. You want to be able to plug and play into different substrate choices and be able to understand early what's the price and what's the performance you're getting. That's explore. Then you want to transition into the design phase. That's really the heavy lifting, going from drawings on a napkin to IP blocks to fully optimized design that's ready for manufacturing. And then you better build it. So manufacture them robustly. Obviously, time to volume, time to revenue, cost, and safety are very important. So we enable the journey for explore, design, and manufacture. What is considered a total solution for the new SoC, or system of chips? In our view, it has three key ingredients. Number one, interface IP that connects the dies together. Number two, design platform that supports the full A to Z design flow from definition to tape out. And number three, enabling of manufacturing and deployment. The first pillar of total solution for SoC is interface IP. That is the building block that connects the die to dies, regardless whether the substrate are 2D, 2.5D, or 3D. For different IP choices, the geometries, the power, the performance will be different. They're going to be conforming to different industry standards. They're going to be having different interfaces, whether it's serial or parallel. But the important thing is there's a menu for you to choose from. Doesn't matter what substrates you have, we'll make it work. The second ingredient is the design platform that enables a chip designer to go from A to Z. You can start from architecture definition to implementation to simulation to verification, and finally having a design that's ready to be manufactured robustly. The third piece, which is going to be a very important section for discussion today, is manufacturing and deployment. Now, at Synopsys, we don't really manufacture chips, but we do what's right to support and enable manufacturing and deployment. There are three pillars to this. The first pillar is the quality of the product. If we're going to make a chip, it better work. The second vector is debug and traceability for the product. It's a physical process technology. Inevitably, something will go wrong. If it goes wrong, how do you debug it? How do you fix it? How do you trace it? And then finally, once the chips are being deployed in the field, whether it's in a car or in a smart city, we want it to be able to optimize the performance and make sure it runs longer. So product quality, product debug and traceability, and in-field optimization, those are the key vectors for manufacturing and deployment enablement. Let's dig really deep into this. Enabling of manufacturing and deployment for the new era of system of chips. If you look at a 3D IC or a system of chips, there are three partitions to it. First are the known good dies, or the building blocks, or the Lego blocks. Second are the interconnects that connect them together. And finally, the whole chip or the whole system together. The quality for all three components are important. So how do we deal with the quality of KGDs, known good dies? A known good die is a chip. So it's going to benefit from the hierarchical nature of the design, but it also inherits some of the problems. Process technology, process variation, circuit design complexity, and a varying degree of product use cases, high temperatures, radiations. So we got to manage all of that. In particular, the way we manage this at Synopsys is to deploy process-aware DFT, for example. For example, for certain types of FinFET, certain categories of faults are more prevalent than the other. So when we design the patterns, we made sure those patterns are process-aware, so you get higher quality. And for the same reason, we have cell-aware DFT and ensure the testing are at speed, at temperature, and power-aware. That gives you the highest quality possible for KGDs. The second piece of product quality was interconnect. how do we test, diagnose, and repair them? In that category, if you look at a general design, the first building block is logic to logic at low speed. These logics are usually connected by TSVs or RDLs. The best methodology to test them are using scans, and it's supported by various IEEE standards, especially 1838. We support static and transition testing. The second type of interconnect is phi to phi, high speed. So, for obvious reasons, BIST becomes more important for high speed or at speed production testing. And because of the high speed nature of the design and the inherent process variations, calibration is important. Inevitably, there will be some broken wires. So detection and repair are important for some of the high speed interconnects, especially for the parallel ones. The third type of interconnect are logic to memory. For example, HBM. We have a methodology to test both the phi and the memory itself. That's how you get high quality on interconnects. What about system? System is a problem that product people need to own. It's usually a trade-off between the cost that you pay now versus the cost you pay in the future. All right, we talked about product quality, which was the first vector of enablement for manufacturing and deployment. Let's talk about the other two. Debug and traceability for product, and in-field for optimization. For debug, really the way we're doing it is by integrating the sensors in the design and performing diagnosis both during ramp and during production. For in-field, we're going to use similar type of data, but the goal is different. Rather than achieving yield, we're going to try to focus on performance optimization and security. And this really is what we at Synopsys call silicon-lifecycle-management, with 4 phases: in design, in ramp, in production, and in field. The key is data. Data coming from the sensors you put in the right chip at the right place at the right time, and the analytics or conclusions you draw at the right time with the right tools, whether it's production or in field. And more importantly, you want to be able to feed the data in both ways to enhance the quality of the product and the reliability of the product. So we have a product portfolio that supports the whole journey from design to ramp to production and field. Let's look at some interesting scenarios. In design and in ramp, this presents a really good opportunity for design optimization. Imagine if you could compare the measured data coming out of the sensors on the chip, which you put in during the design phase, to the testing results. That'll give you a great opportunity to reduce the margin and hence a better design that runs at a faster performance and possibly a lower power. That's a design optimization. What about test optimization, both during initial ramp and during production? Imagine if you could correlate the sensor data with the test result at a bigger scale on the whole chip. That gives you an opportunity to identify the outliers and fix the problems and increase the overall quality of the product. And finally, with the age of autonomous driving and IoT and everything that's happening, there's going to be a lot of things with chips in it. They're going to be on the road, or they're going to be in air, they're going to be connected. We really want to be able to provide a tool to you so that you can optimize the performance based on data in a secure way. And that's what in-field performance optimization really means. Ultimately, it goes back to the data you get from the sensor and all the toolings, the mechanisms you use to collect the data, to analyze the data, to transmit the data, and to adaptively control the circuits. The question you should have really asked about silicon lifecycle management is, why is it even relevant to Systemofchips or 3D IC? Well, it is because Systemofchips or 3D IC is a really big chip with a lot of complexity. So that's very important. Now, let me recap. I just talked about solution for the new SoC or Systemofchips. It has 3 key ingredients: interface IP that connects the die and die together, design platform that enables the creation journey from A to Z, from architecture to analysis and to sign off. And finally, manufacturing, the excitement of making system of chips. We help you ensure product quality. We help you debug and trace issues when it arises. We help you ensure there's a mechanism to optimize the products even if they go into the field. That is the solution for a system of chips. So what is the journey ahead on this SysMoore journey? A lot of things we need to collaborate on as an industry. There are several remaining challenges. One thing I could think of is, wouldn't it be really nice to have an assembly design kit that include mechanical, photonic, electrical, and thermal properties? And wouldn't it be nice if we have a standard for ensuring supply chain security? Well, it's not to say the current supply chain is not secure. It's just that with 3D IC or advanced packaging or system of chips, the supply chain is getting more complicated. The value of having built-in security for the supply chain will be higher. Inline process control were often taken for granted for monolithic chip creation. I think it's going to be more relevant for advanced packaging. Well, as I just said, 3D IC is a really complex and really big chip. So the value of providing data feed forward and feed backward during the entire product lifecycle is even greater compared to a simpler monolithic chip. But we better do it with trust among multiple vendors and multiple system OEMs. This is a really exciting time. We're seeing different technologies coming to fruition. We're seeing heterogeneous integration of chiplets. We're seeing super monolithic integration of emerging devices such as nanowire. We're seeing hybrid architecture that attempts to combine the strengths of heterogeneous and monolithic integration. Technology is giving us chip designer wings. And EDA is going to help chip designers create more chips faster. And I look forward to the next 1000x of transistors per SoC and increase of the quality of the product. And more importantly, more and more people can really innovate on chip design. Thank you.